Okay, I guess that we can start. So good morning or good afternoon to everyone. Thank you for joining the LSI Lastem webinar on G.Re.T.A system, electrical resistivity tomography for tailings and air dams monitoring. My name is Federico Orlando. I work in the LSI Lastem International Sales Department, and I will be your host today. Let me start by saying that we are truly thrilled by the success of this event. We have received more than 200 registrations from 31 different countries, proving that there is a great interest in this topic. So before handing it over to Greta Tresoldi, who is going to be the main speaker of this session today, I'd like to share a few housekeeping notes. So at the end of Greta's presentation, we will have a question and answer session. Given the high number of attendants, I kindly ask you to submit your question at any time using the chat. I will do my best to address as many as possible. And don't worry if we don't manage to answer your question live, we will get back to you via email. Also, this webinar is being recorded and the registration will be available on the LSI Lastem YouTube channel. So that's all from my side for now. I am delighted to invite Greta Tresoldi, Product and Marketing Manager at LSI Lastem, to take the stage and guide us through the fascinating world of ERT for tailings and air dams monitoring. So thank you, Greta.
Good morning and good afternoon to all the audience from all over the world, and thank you very much, Federico, for the presentation. I'm Greta Tresoldi, Product and Marketing Manager from LSI Lastem, and today together we will delve inside the topic of electrical resistivity tomography, ERT, applied for tailings and their dam monitoring. Then we will focus on the G.Re.T.A system, georesistivimeter for time-lapse analysis, and we will see some results from interesting case studies. But it's good to start from the basis. So ERT methods belongs to geophysical measurements. So just a brief introduction about this kind of measurements. So some key points. First of all the geophysical measurements are non-invasive, so you can retrieve information about the subsoil without excavating or coring. All these methods are based on the physical properties of the soil. And so thanks to these indirect measurements, you can have the soil characteristics with different methodologies. So in the family of geophysical measurements, we have seismic, electromagnetic, gravimetric, and electrical methods. These methods can be divided into passive, where it's possible to detect variation within the natural fields associated with the earth without transmitting any signal in the ground, or active methods, where there are some artificially generated signals that are transmitted inside the ground. The ground acts like a filter and modifies the received signal. So thanks to the propagation of this field inside the soil, inside the material, it's possible to retrieve some information through the way these waves travel inside the soil. So the ERT measurements are electrical methods and they are active. So we are injecting an electrical current inside the soil artificially, and we are receiving a signal in terms of voltage from which we can retrieve the resistivity value. So how does it work? How is the operating principle of electrical resistivity tomography measurements? First of all, as previously said, these measurements are geophysical indirect measurements based on the electrical field propagation that is different based on different soil properties. Thanks to this injection of current and measuring of voltage, is it possible to reconstruct a bidimensional picture of the soil electrical properties. So, which is the main electrical property of the soil is the resistivity. And why is it so important for us? Because the electrical behavior of the soil is related to the soil composition, mainly the water content in a given soil, the presence of voids, and the fluid resistivity. These kind of measurements have been invented in the mid-90s, but so far have been applied mainly for spot measurements, so only one measurements with portable systems. How does these measurements work? You need a G.Re.T.A, so a machine and hardware part with electrodes. These electrodes can inject the current inside the soil, and then you need cables to connect the hardware. We have multiple electrodes, and so we can use 4 of them each time to obtain one single point of resistivity. So we can see here in this right part, we have a resistivity section that is obtained using different quadruples each time. So changing 4 electrodes each time, we can obtain resistivity value at different depths, for example, or different position. What we use is the Venner configuration. So we inject current into electrodes, the current electrodes, and we measure voltage at the voltage electrodes. So you can obtain in this way the raw value of apparent resistivity thanks to the second law of Ohm. Then you need to invert the data thanks to a tomographic inversion that is an iterative process. At that time, you can obtain the inverted data that is like a picture of the underground in terms of resistivity. So which are the main pros of this kind of measurements? First of all, that they are strictly related to the water content. So resistivity is a good proxy of water content. The resistivity section is bidimensional, so it's not a single point measure, but is a section of large area. In this case, you can see here 141 meter the profile and 22.5 meter of depth. So you can retrieve information on large investigated zones, and you don't need to core. So, but now we are speaking not only about E.R.T. measures, we are speaking about automatic E.R.T. monitoring, because the G.Re.T.A system works with monitoring over time. So which are the main pros of automatic E.R.T. monitoring? First of all, that the system is fixed, and so you need to install it only the first time with a standardized procedure. We are monitoring over time, so the most important aspect is the evolution of the processes related mainly in a given soil to water infiltration. The inversion procedure, that is quite heavy to do, is totally automated. So it's done on the cloud platform, and the user don't need to do this manually. So it's really, really handy for the user. Then also the configuration of the measurements is fully automated, and you can do it from remote without going on site. So what can you do with the automatic E.R.T. monitoring? You can follow the triggering and evolution of underground processes over time. So they can help preventing some problems before it's too late, because if you see the result, so for example the displacement, it's too late because the process is already ongoing. A step forward, so how we can use E.R.T. for TSF monitoring. Geoelectrical monitoring offers valuable insights for different water-related processes. So identifying concentrated seepages, detect the underseepage, analyze the saturation over time, and not only in saturated zone, but also in partially and unsaturated soil, because the electrical current can travel also in the unsaturated soil, so can provide information on the percentage water content in the unsaturated soil. So it's possible to monitor this saturation over time and assess different processes such as the dewatering or evolution of groundwater level. All these processes are connected to the assessment of the stability of the structure over time. So focus on the G.Re.T.A system. What is that? It's an off-the-shelf, autonomous, cloud-based, fully automated georesistivity meter that we specifically designed to be permanently installed to perform G.R.T monitoring. The system is composed of different parts. We have an hardware part, mainly the box, the cables, the electrodes. Then we have the cloud software, because the system is always in connection with the cloud platform. And then we have the visualization. The data can be accessed thanks to a laptop, mobile, also on the field. Some features, the remote programming. So the system can be programmed also from remote. The system can provide real-time data, and as I previously said, the data inversion is totally automated. The system is based on a cloud platform, and this cloud platform can be also integrated in other third-party platforms thanks to APIs, or can host inside itself other data coming from a meteo station or piezometers directly connected to the system or through APIs. We will see later on. So what are the advantages of the G.R.E.T.A system? First of all, one of the most important is the estimation of the water content. Since resistivity and water content are inversely related, mainly higher the resistivity, lower the water content, and vice versa, in a given soil, because we are installing a system in a given spot, resistivity changes are mainly related to water content variation. In homogeneous soil, or soils that are composed by the same material, like most of the ETSF, resistivity is thus an excellent proxy of water content. So the G.R.E.T.A system can assess changes in water content and can help to proactively predict the creation of possible seepages, infiltration, other kind of anomalies that may become a risk to the structural integrity of the tailing or earth dams or levee water dams. So this system can be applied also to other earthen structures. Here we have a scheme that I think is really useful to understand better this point. This is a section from a site that we have in South Africa. We can easily recognize that there is a surface part with these red values. So if we check the color scheme, we see that red values means high resistivity. So high resistivity means lower water content, so the soil is more dry. In this bottom part, we have these blue values that corresponds to really low resistivity value. And the low resistivity values are related to higher water content, so the soil here is probably saturated. And here we can easily recognize this line, this phreatic surface, between the dry and saturated part. Other advantages, for sure, the fact that the system can be configured to perform early warning. The system is fixed, it's self-powered, it's installed in a given soil, and so it enables continuous monitoring of the soil resistivity changes over time. But it is also possible to set up some alert thresholds. So in order to be alerted with an email if there are some variations in water content, onset of seepages, formation of fractures, and so when these predefined thresholds are exceeded, automated alerts can be triggered. Other advantages are related to the comprehensive information that the system can provide. As previously said, the system can provide information in a big area, it has an extensive data coverage, unlike other monitoring equipment such as piezometer, which provide only punctual measurement. The G.R.E.T.A system delivers soil insights along extensive profiles, usually hundreds of meters long and tens of meters deep. Another important point is the enhanced water content monitoring, because the G.R.E.T.A system can provide information not only on the position of the water table, but also on the estimation of soil moisture percentage, even in unsaturated condition. All these points are related to the proactive risk detection, because since we are analyzing the processes ongoing in the underground, we can predict and mitigate the risk before they happen, unlike other monitoring equipment that are related to the analysis of displacement, for example, that is the result, for example, of the seepage. The system is really easy to use, and also the installation is really fast. You don't need to drill or core, and so the system is set up with a minimal effort. Here you can see some pictures and scheme about the hardware part that is composed of an IP66 box. Inside the box there are different modules that is really good for maintenance. We have the 4G modem router for communication, and we have the battery that is charged by the solar panel. It's not mandatory. You can also plug the system with the local electric grid. And the system has 2 cables with 48 electrodes. Speaking about electrodes, we have 2 types of electrodes based on the 2 types of installation that we can guarantee. For a permanent installation or long-term installation, the best electrodes to be used are the stainless steel plate electrodes. These electrodes are inserted in a small trench, shallow trench, and then the cables and electrodes are covered so that they are safe and they cannot be damaged. In opposite way, you can use road electrodes for temporary installation. We are always speaking about monitoring, so not for single measurements, but for, I don't know, some month of monitoring. So these stainless steel road electrodes are hammered inside the soil. The fact is that the cable remains uncovered, it remains on the surface, and so can be damaged by people, animals, or machinery. Going to the second part of the system, the cloud platform. This platform is really useful to obviously visualize the data, make some processing, make analysis, but also to configure the system. In the home page, the user can geolocalize the station, can upload pictures, documents, and other metadata. The visualization part is related to the visualization of resistivity section, both inverted and apparent. Obviously, it's possible to change some parameters related to the picture, the color scheme, the visualization. Here you have some information about the system, about the configuration, the iteration, and here you have this calendar to browse for different measurements and compare them. So it's possible to manually compare different sessions of different days. The third image is the percentage variation of resistivity. Here, for example, we have one data before the rain, the second data after the rain, and this blue part is the negative variation due to the infiltration of rainwater inside the soil, and so the fact that the soil now is more wet. Is it possible to download the data? The platform is totally open, so the download can be done manually, file by file, or with a selection of a period massively. The export can be done also automatically, so through APIs is it possible to extract all the data to other software. Visualizing the data, is it possible to make some quick analysis? So select an area and retrieve the minimum, maximum, and average value in the section. We have then another part related to time lapse, so more full of options and features. You can select on the map a part of the section And then you will have the graph of the evolution of average resistivity of this particular part of the section over time. What you can do is to compare the data with rainfall data, for example, or with piezometric data. The configuration of the system can be done directly from the cloud platform, so you don't need to go on site to configure the device, to change the frequency, to change the parameter. You can change everything from the platform, and then you can send to the device. Alarm setting. As I said, you can select different logics and put some thresholds based on percentage change of resistivity or on absolute value. So you select an area, the surface, the bottom part, the saturated part, and you can put different logics. We will see later on in the demo. Is it possible to integrate also additional data coming from sensors that are directly connected to the G.Re.T.A system or coming from other platforms? So we can integrate, like in this case, the rainfall, the temperature, or other environmental variables thanks to APIs and also piezometric data. In this case, at site, we have 2 piezometers, and this is the groundwater level indicated by the piezometer that corresponds really well with the boundary between these 2 completely different zones, the saturated and the dry part. The system can be also calibrated through core samples. So you need to do a core at site near the profile, extract different core samples at different depths, take the samples to the lab, measure directly the water content, and you can insert in the platform this curve that relates the 2 variables. And then you will obtain an estimation of water content, and you can visualize this section. Okay, we are halfway in the presentation. Now we are in the case studies part. I think it's really, really interesting. We have many installations all around the world, also in other fields of application, river levees, landslides. In this presentation, I report our installation in the tailings world. So we have an installation. We had an installation in a copper mine in Chile, one in a gold mine in South Africa, another one in a bauxite mine in Australia, in a platinum mine in South Africa, and the last one in December in an iron mine in Brazil. Okay, the one that we are analyzing now is the gold mine in South Africa. Since it's the first one, I want to spend some words about the different steps for the installation. So the installation is really easy and standardized, and the steps are always the same. The step 0 to be done in the office is the configuration of the modem router with the local SIM card. Then on the field, we have the step 1, so the plinth installation and the trench excavation. So here in the picture, you see a big machinery, but at site they had this big machinery, but the trench can be really smaller and shallower. You will see in other installation. Step 2 is the box and solar panel mounting. You can see here that the system was installed on the crest of a dam, and the objective was the analysis of the evolution of rainwater infiltration and possible seepage detection. Step 3 is the cables laid down and the electrodes assembly. Here you can appreciate how big is the trench compared to the cable and the electrodes. These are the stainless steel plate electrodes. In this case, the distance between the electrodes is of 3 meters, with the total profile length of 141 meters and the total profile depth of 22.5 meters. The step 4 is really crucial and important. You need to cover really well the electrodes with soil, bentonite, and water, because they need to stay in good contact with the soil in order to inject the right amount of current to perform a good quality measurement. So the step 5 is related, is the contact resistance test. So we can perform this diagnostic test thanks to our platform. These are the number of electrodes from 0 to 47, and the R value is the resistance between one electrode and all the other electrodes in parallel. So we are testing the circuit. We are testing if the current is flowing well in the soil. Step 6 is the trench closure, and then once turned on, the system automatically sends the measurements to the cloud platform. The site at this gold mine in South Africa was really homogeneous. You can see the values of resistivity that ranges between 15 and 35, so really close to each other. But we can appreciate, for example, that the surface is a little bit more wet. We see these blue values, lower values. And we know that at site, the phreatic level that corresponds to 25 ohm per meter, it's almost at 15 meter depth. We don't have a piezometer at site, but we can recognize. Here, just an example of a comparison, this site before the rain and after the rain. The percentage variation shows that there is this negative variation at the surface corresponding to the infiltration of the rainwater. We can also appreciate, for example, here after meter 40, that rainfall water is infiltrating up to 10 meter of depth. Okay, another case studies is tailings dam monitoring in a bauxite mine in Australia. The steps of the installation are always the same, but you can appreciate how is the trench here, really small, really shallow. In this case, the facility was closed. It's a closed post-closure facility. The pond is capped, and the user wanted to assess the dewatering of an embankment downstream the dam. So here all the picture related to the installation, always the same steps. The contact resistance, really low at site. It means that the electrodes are working really well because these values are below 1000, so they are really, really good. So this is one of the results at site. You have already seen this picture. In the site we have 2 piezometers, and we can see that all the resistivity values below 4 meters are extremely low, between 1 to 3 ohm per meter, because the material and the saturation. The surface is drier, but the values are quite low indeed, while we have a partially saturated part, this green part. We also could spot a zone in the surface with a higher water content, probably a filtration, a seepage in the embankment. What we did at site was a 1-year time-lapse analysis to assess the dewatering of the embankment, focusing on the superficial part, so the first 4 meters of the cross-section. Here you can see the average value of resistivity of the first 4 meters along 1 year, plot with along with the rainfall at site. So we can see that in the first part, first month of installation was a dry period, and the resistivity was increasing because the relationship is inverse. Then we have a quite stable period between October and December. Then the wet season started, and we had this drop in resistivity, meaning that the surface part is getting wet. But after the end of the rainy period, the resistivity increased again. And after 1 year, we could assess the plus 25% in resistivity, meaning that the watering process was good and the soil now is drier than the year before. Here we have another case studies, is a platinum mine in South Africa. The installation in this case was performed on a bench of the tailings dam, and the objective was the analysis of water content, seepage, and also the change in the water content related to climate change, because we have analyzed different periods with really extreme drought and a period with extreme rainfall, and you will see the results. Here again, the installation of the cables, the coverage of the electrodes, contact resistance test. Here, these values are a little bit higher, but still okay. What you can also check in the platform is the quality of the data. So not only the contact resistance, that is one diagnostic tool, but also the standard deviation of the measurement. So this is the shape of the section, and every point in the section is measured not only one time, each measurement, but they are measured many times, and then a statistic is done to retrieve the average value and the standard deviation. So if the standard deviation is low, like in this case, it means that the measurements are really stable. Also, you have another parameter that can be used to assess the quality of the result, that is the RMS of the iterative procedure of the inversion process. Also here we have really low value of RMS. If this value is below 5 and 10, the inversion procedure was performed in a good way. Okay, this is the inverted resistivity visualized using the contour plot. Here you can appreciate that there is a high vertical stratification with high values of resistivity in this surface part and really low value of resistivity in the bottom part below 10 meters. Also here there is a critical zone to be monitored with higher water content. At site we don't have a piezometer, but the blue part is likely saturated due to this low value of resistivity. As said, the year 2023-2024 were of extreme drought at site, so no rainfall for almost 1 year and a half. And so this is the result the day of installation, August 5, 2023. This is the result after this period of extreme drought, January 2025. So also visually, you can appreciate that the resistivity are increased a lot. And this difference said that the increase was of 400%. Also, the groundwater, the phreatic level was dropping down a few meters. Then the month of January and February were really wet, so a lot of rain fall at site. And we can compare now the data of January 2025 with the data after rain. We can see that the situation is really different. The resistivity has lowered a lot, and also the difference says that there is a decrease of 80%, and this blue part is the infiltration of water. The infiltration is up to 15 meters below ground. So comparing the starting situation and the last situation, we can see that the surface part is more wet because we have rain at site, but the medium part is still more dry than the starting of the monitoring. With this platform, we can also perform this time-lapse analysis obtaining this kind of graph, so the average, minimum, maximum value of some parts of the section over time. Here, the same period from January to almost now of the surface. We can see the decreasing of resistivity thanks to the wet season. Also below, between 5 and 10 meters, we can appreciate the same behavior. So also here rain is infiltrating and resistivity is decreasing. The last case studies is iron mine in Brazil. We performed the installation in December, and the objective was the assessing of a known seepage downstream a dam. So we installed the system, and what we could spot is this seepage that will be monitored over time. Here we can also see the apparent resistivity, so the data before the inversion. Here the values are really high because of the material, and we can see these conductive zones every 10 meters. Then we will see that they are related to artificial material present at site, probably metallic pipes. And the standard deviations of the measurements are really low, so the measurements are of good quality. These are two visualizations of the same data, so the inverted resistivity that can be visualized thanks to heat maps or contour plot. In any case, you can easily recognize this central bottom part with really low value of resistivity related to higher water content. This is the position of the seepage, so this part is really critical and needs to be monitored. Okay, conclusion. We have seen that geoelectrical measurements can provide really useful information for tailings and earth dams, for the management and the recognition of seepage, saturation, the watering processes, all these processes that are related to change in water content because of this relation between resistivity and water content. Then we did a step forward, so we analyze and we saw together the geoelectrical automatic monitoring over time. It's really important if you want to follow the evolution of these underground water-related processes in real time. The G.Re.T.A system is an effective and innovative off-the-shelf solution, and it is a strong opportunity for the mining industry to improve the monitoring of TSF over time as requested by the GISTM. Now we will go for a demo of the software, and then we will give the floor to Federico for the Q&A part. Okay, here we have the platform. This is the home page. So in the home page, the user can localize its own system, these green dots, and clicking on the dot, the platform zoom in the installation of the system, the spot. This is the case in Australia with the CAPS facility. This black dot is the position of the system. Here you can see some information, and also you can upload and download pictures and files. Clicking directly on the cables, this yellow part, you are redirected to the data. So here you have the inverted data. You can move here the cursor and see the values. What you can do is you can change minimum maximum value of the scale, or you can also see the apparent resistivity, so the data before the inversion. And also you can check the other parameters such as the injected current, the measured voltage, standard deviation, and if you have the correlation with water content, you can also see the water content. In this site, we have as you have already seen, we have additional data. So we have piezometers, and we have also rainfall. So now at site is not raining, but yesterday I think was raining. Here we have the name of the piezometer and the position of the groundwater table directly on the map. You can also perform some quick analysis, select an area, see the minimum, maximum, and average value. And what you can do is also you can download manually this data, or after in the analysis, you can massively download many data together. Then you can also compare and browse for different measurements. We can compare, for example, these two data. And here we have this change in resistivity. You see a lot of colors, blue, red, but if you look at the values, they are really, really low. So 1%, 2%, 3%, below 5%, the situation is stable. So in this case, between these 2 days, the situation was really, really stable. Then another important part is the contact survey. So as I told you, is a diagnostic tool to check if the electrodes are working well. And here you can see that these are the numbers of electrodes between 0 and 27. And these R value are really, really low because these values are good if they are below 1000, but we have 50, 70, so really good functioning of the electrodes. As I said, you can also configure a system. You select your system, you can change some information, the latitude and longitude, but also the scheduling of all the measurements. So the contact test, usually we do 1 per week. The resistivity measurements, usually we do 1 or 2 per day. And you can send all the modification to the device without going on site. The really important part is the analysis. As I told you, you can select your site and you can perform some time-lapse analysis. You can select the period of time. We can select from the 1st of January to the end of February. You can fetch the session, and here you have all the measurement. In this case, we perform 1 measurement per day. You select the measurement and you can massively download them, or you can perform some standard deviation analysis. So, for example, analyze how standard deviation have changed during your period. This is for sure the most important part. You can perform time-lapse analysis. So you select an area. For example, we can select this partially saturated part close to the saturation. And then we can send a request. So test partially saturated zone. We create the request, and here we have all our tests that are performed. For example, this is one that I did this morning in the other webinar. Here you can appreciate the evolution of the average, minimum, and maximum values in the period. This is the case where the last 2 months were really wet with a lot of rain, so you can see that the average is dropping down. You can download the graph, you can download also the file, and I think that now our analysis is complete. And so here we can see a little bit different because we selected another area, not the surface, but the partially saturated part. Then we have the alarm part. Selecting your site, you can create a new configuration. So we can set test alert, select the fact that this alarm is a warning, and then we can include all the people that can receive emails when these thresholds are passed. Then I can select different evaluation areas. So for example, I can create a logic for the surface. So in the surface, I don't know, I can choose to verify my variation, percentage variation. So alert me if the resistivity changes of 50%, not only 1 point, but at least 3, and compare the data of today with the data of yesterday, no matter if one data is missing. Then I can, for example, add another area. So for example, the partially saturated area. And for that area, I can select a verification based on the absolute value. So for example, I know that the saturation, the saturated area has a resistivity of 30%. I can decide to be alerted in this part if the resistivity is less than 30. So it means that it is now saturated. Then I can save. I can create also different alerts based on different periods of the year. So summer season, winter season. Here I have all the archive of my past alerts. Then I have a diagnostic part and a company and administration part. So more administrative part. You can create a new user with different access. You can create the licenses, see your station. So it's more administrative part. So I think now it's time for Q&A. So I pass the ball to Federico. Thank you very much.
Thank you, Greta. It was very, very interesting, really. So as you said, now it's time for question and answer. So I'd like to start saying that we have received many, many questions, and it won't be possible to read all of them, but I will do my best to summarize the questions. So I would like to ask kindly Andrea Certo to join us. And yes, so the first one, Carlos. Carlos is asking, how can I monitor a dam that is 1 kilometer long? So I guess that probably Greta, you can answer this one, please.
Okay, thank you very much, Carlos, for the question. Yeah, you can monitor profiles that are longer than the single system using and installing different systems. So you can install different systems one after the other, and then you will see in the same platform, in the same session, you will see your system. So it will be really easy to select one system or the other also on the map, because you will see the position of the system and also the position of the cables. Obviously, to choose the right number of systems to be used, in this case for 1 kilometer, you need to answer some questions. So you need to assess the characteristics of the soil and also what you want to measure. So for example, are there in your dam some critical areas that you want to monitor more than others? Or which depth is the one that you want to reach? Or I think also which is the characteristic of the soil at site? And also, yeah, it depends mainly on what you also want to have, like, for example, resolution, if you want more resolution or less spatial resolution. I think that depending on these questions, the number of systems that can be used to cover 1 kilometer can vary between 3, 4, and 8. It depends on these characteristic. Thank you.
Okay, thank you. Now, I see that there are several questions related to how the system is offered on the market and about the business model. So I think that Andrea Certo, CEO of LSI Lastem, would be the best person to answer this question. So please, Andrea.
Thank you, Federico. Good morning, everybody. Well, in general, in every country, we try to work with local distributors that not only sell the equipment, but also provide the installation and the maintenance services after that. In the initial price of the equipment, the first year of the software license fee is included. And then from the second year onward, the customer pays an annual subscription to use the cloud platform. That includes also all future software upgrades and improvements. Some local distributors, like in Brazil, for instance, as an alternative to the sales of the equipment, they offer a kind of monthly, long-term, full rental scheme. But this is very much up to the local distributor to decide whether to offer such a rental scheme or not. Let me also clarify that we, as LSI Lastem, we are not offering data interpretation or consultancy services. We, as LSI Lastem, are only a technology provider. For insight data analysis or interpretation, we leave it to the final customer or the engineer of record or other specialized consultants that have a comprehensive view about what is going on at the site. I hope I have covered most of it.
Yes, thank you. Thank you very much, Andrea. I have another question here from the audience for Greta, and it is how it is possible to convert resistivity measurements into water content. Is it mandatory to do core at site? So please, Greta.
Okay, thank you. Thank you very much for the question. So the correlation between resistivity and water content in this kind of soils is quite easy. You don't need every time to perform a core to calibrate the system. As you have already seen in some case studies, if the G.R.T. section reaches the water table, it's quite easy to identify which is the resistivity value of the saturation. If you have a piezometer on site, obviously you can also correlate piezometric data with the resistivity data. Obviously, if you want to convert the resistivity section into a water content section inside the platform, you need to do a core, extract the samples, go to the lab, and then you can insert this function inside the platform and you will retrieve directly the estimation of water content visualizing the map.
Okay, amazing. Thank you very much, Greta. And I think that we still have time for a couple of more questions. So going through the chat, I see Henry is asking, is 22.5 the highest depth that can be achieved with the G.R.E.T.A system?
Okay,
So
thank you. Thank you very much,
yes,
Harry, for the question. No, 22.5 meter is not the maximum depth that the system can reach. Usually, the standard system that we know that with this amount of current that we inject maximum 400 milliampere because it's an autonomous system with solar panels, so the amount of current that can be injected is limited. With this amount of current, we can reach 22.5 meter almost in every kind of soil, resistive, conductive, but because in some cases, if the characteristics of the soil are known, we can also try to implement longer distances between the electrodes because the depth of investigation is related to the distance between the first and the last electrodes. So if we increase the distance between the electrodes, we can also increase the maximum investigation depth. So in some soils that are not too much resistive or too conductive, we can also implement 5 meter between the electrodes so that the maximum investigation depth can be of 40 meter.
Okay, perfect. Thank you, Greta. I think that we can go for the last question. I see that Orlin is asking us, how can the different layers and construction of the tailings wall affect the measurements? Different gravel materials, drainage system, and geocomposite layers.
Okay, thank you, Arlene, for the question. Obviously, if you have different material inside the dam, you will measure different resistivities, because resistivity is related also to the type of material. What you are analyzing with the time-lapse analysis is the variation. So you can appreciate different variations in the different material because the site is always the same. Obviously, if you have a liner or a plastic tarp, you need to put the electrodes below this tarp because the current cannot pass through this liner. If you have some metallic elements, they can negatively affect the measurement. So it's better to check. If you have metallic pipes, it's better not to install the system near these artificial structures. Thank you.
Okay, perfect. All right, ladies and gentlemen, we have now reached the end of our webinar. As I mentioned earlier, if your question was not answered live, don't worry, we will reach out via email, so we will answer all the questions in the chat. Additionally, I'd like to add that a PDF copy of today's slides will be shared with all participants shortly, and inside you will also find the contact of Greta Tresoldi and Andrea Certo, should you wish to reach out for further clarification, discuss your project needs, or request a quotation. I would also like to take this opportunity to inform you that LSI Lastem will be showcasing the G.Re.T.A system at 4 major events worldwide in the coming months. So we will be in Chengdu, China in May 19 to 23 at the IT International Conference. We will be in Brisbane, Australia in July 29 to the 30 at the 2025 Mine Waste and Tailing Conference. We will be in Santiago, Chile in September 3 to 5 at the Tailings 2025 conference, and we will be in Banff, Canada in November 2 to 5 at the Tailings and Mine Waste 2025 conference. So on behalf of LSI Lastem, I would like to sincerely thank all of you for joining this webinar, and we are thrilled to be to the level of engagement and hope you find it interesting, valuable, and insightful. So we truly look forward to work with you and to help you with some of your projects. So please feel free to reach out anytime. So thank you once again, and arrivederci.